Hello, my name is Marshall Monsivais, and I'll be presenting with my colleague, Miguel Angel Trevino. We worked on this project under the guidance of our supervisor, Dr. Mustafa Al-Lail. And we also want to thank the National Science Foundation and TAMIU's Act on Ideas program for supporting this project. So Towards a Software System for Spatial Temporal Authorization is a project that's focused on using the spatial and temporal components of a user, or as I say, the location and time of them, and using that to determine resource access. So authorization in this context would mean the process of looking at a user's information and determining access to resources. So for this project, here's the outline for the things we'll discuss in the presentation. We're going to discuss the problem we're facing and the solution we have for it. We're going to give an overview of GSTR-BAC, which is the authorization model our project is based on. Then we'll go ahead and discuss the main contribution of this project, which is the software architecture and the main components within it. After which we'll go ahead and discuss a realistic example of this model in a business setting, and then we'll go ahead and conclude this presentation. So the problem we're facing stems from the fact that there's now many new ways to access information online. Many entities from offices, hospitals, governments, and even more rely on being able to reliably access information online. And one of the ways they can do so is they can use things like mobile apps to try and access information from multiple locations. But something that we need to also consider is the fact that this means there's also many new ways to compromise information online. There's at least 5,000, there were 5,183 breaches in 2019, and at least 7.9 billion records exposed in 2019 by September alone. Something we want to investigate then with our project is we wanted to see if mobile devices could be a potential cause for this increase in breaches, considering the security risks they can pose. Mobile devices are susceptible to theft, tampering, or even just having information accessed in times and locations they shouldn't be accessed in. For our project, we wanted to look at location and time in determining access to resources. So here we have an example for how location could be used to combat illegitimate access attempts. So let's say there's a policy where only doctors in a hospital should have access to medical records. If a doctor tried to access those medical records from within a hospital, the system would grant access to them. But if the doctor tried to access those records from outside the hospital, let's say from their home, the system will go ahead and deny them. And if they were to ask, well, why can't I access the medical records? It's because they're not an authorized location. And the same can go for time, where let's say the policy is that doctors should only be able to access medical records while in the daytime. So if a doctor tried to access those records in the daytime, the system would grant them access. If the doctor tried to access those records during the nighttime, the system would go ahead and deny them. And if they were to ask, well, why can't I access the records? It's because they're not trying to access them during the approved time period. And so these factors of time and location can be customized based on the role of the individual or the resources requested. So that would mean that something like an office manager might have different access permissions than an office worker. So for related work, we wanted to look for something that would help determine authorization for this system. So we looked first at the role-based access control model. Role-based access control, or RBAC, which is an industry standard method of access control. RBAC uses the user's credentials or their role in the system in order to determine resource access. And so what that means is the role is something like a manager, a clerk, or an accountant, something like that. And the system would use that in order to determine whether a person would have access to resources. But something to consider with RBAC is that it does not inherently consider time and location. Multiple extensions created by other computer scientists exist that attempt to utilize time and location, some of which can be found in the references section of this presentation. But the one we want to look at is the Generalized Spatial Temporal Role-Based Access Control Model, or GSTR-BAC, since that's the model we based our research on. It uses time and it uses location in order to determine authorization requests. So our objective for this project then is we want to be able to create a GST-RBAC-based software system that uses time, location, and the user's credentials in order to determine resource access. So our contributions for this project then is a software architecture based on the GST-RBAC model and an implementation of that same software architecture. Before we talk about the implementation of this architecture, however, we need to discuss how GST-RBAC actually functions. GST-RBAC incorporates time and location in access control decisions. And so it will use time, which is represented by time instances, and it'll use location, which is represented by GPS data, both of which are obtained from the user's mobile device. Time is recognized as a time interval. And so what that means is, let's say a period of time from, let's say 2 o'clock to 5 o'clock. So if a user tries to access the resources from within that time span, they will be granted access. And so something similar will occur for location, where there's an authorized area that a user can request access from. So if they request access to resources from within an authorized area, they will be granted access by the system. And so GST-RBAC will use both of these properties in addition to the user's role to determine whether or not they should have access to resources. Here we have a conceptual diagram of GST-RBAC that divides it into the components that make it up. Here we have a set of users, which can be assigned roles and ST zones, and they represent the people that are using the system. So users have the ability to move around, which means that our system needs to be able to track them since their times and locations will be constantly changing. So, and we need to be able to determine whether or not they should have access to resources based on their current time and location or their current zone. ST zones then are comprised of time span and location. There can be multiple ST zones with different times and locations, meaning that users may have different times and locations from which they may access resources. Additionally, we have a set of roles, which can be assigned permissions and ST zones. And again, roles represent positions in the system. So things like manager, cashier, accountant. And they also have, and since they have different permissions, that means they have, and since roles have different permissions, that means that they have different resources that can be accessed and actions they can take. So what that means is for each role will have a different permission assigned to it that will show what kind of resources they are actually able to interact with and how they can interact with them. And that means that each user has a different role that denotes what kind of things they can do within the system. And there's also additional aspects of GST-RBAC like role hierarchy, which is denoted RH, and that represents how certain roles are arranged in the system. And then we also have separation of duty, which is denoted here as SOD. That ensures that only certain roles are active at the same time. And both of these aspects are elaborated on more in detail in the original paper of the GST-RBAC model, which we also have linked at the end of this presentation in the references section. So now that we've given an overview of GST-RBAC, we can go ahead and discuss the software architecture that we've implemented. We represent that architecture here using the Unified Modeling Language, or UML, which is used to model software design and interactions within systems. So here we use the UML component diagram, which shows how the different components in this system are connected to each other and how they communicate with each other. So here we have three main components: mobile application, a resource server, and an authorization server. And we also have one external component, which is a GPS, and that supplies location information to the mobile application. And we'll go ahead and talk about the responsibilities of these components a little bit later into the presentation. But first, let's discuss how the system handles resource requests using a UML sequence diagram. What a sequence diagram does is it shows how the different components interact with each other and communicate with each other to perform tasks. So in the sequence diagram, the user will first log into the system. And if they successfully log in, they'll go ahead and be able to request a role activation. And so what that means is they're requesting access to a resource. So when the resource server receives this request, it'll send a request for an authorization token to the authorization server. And when it receives a response, there's a few different things that can happen from there. The first thing is if the request is granted, the mobile application will receive an authorization token and will receive the requested resource. But something to note, however, is that if a user moves out of a valid ST zone after having received access to resources, they'll have their access terminated and they'll have their privileges revoked. And what that means is they will lose access to the resources they were accessing before. And the reason this happens is because there's an ongoing process of authorization occurring here, where the system will constantly be checking to make sure that a user is in a valid time and a valid location. So if they ever leave a valid time or a valid location to somewhere that is invalid, the system will detect that and it'll revoke their access to resources until they return to a valid time and location. And the other possibility that could have happened here was that the request was denied outright, in which case the user was never granted access to the resources because they weren't in a authorized time and location. And so at the end of this, regardless of what case happens before, the user may log out of the system when they are done using it. Having gone over how the different components interact with each other in order to handle resource requests, it's also important to note how authorization is actually carried out within the system. So a user will go ahead and make a resource request, and when they do so, it'll trigger the policy information point to send policy information to the policy decision point. So what the policy information point does is it just stores that information, so it can later give it to the policy decision point. The policy decision point will take the policy information it receives, and it will also take the user's time and location, and it'll compare those two things in order to determine whether or not a user should have access to resources. And so depending on its decision, it'll go ahead and send that decision to the policy enforcement point. The policy enforcement point will then look at the decision that was made and enact the whatever it has to based on that. So if the policy decision point says to grant access to resources, the policy enforcement point will go ahead and distribute the requested resource. And if the policy decision point said to not distribute the resource, the policy enforcement point will simply not distribute the resource. So having gone over how the different components interact and how authorization is carried out within the system, we can go ahead and talk about the three components in a bit more detail. So here we have the mobile application, and we can see it's divided into multiple subcomponents that show how the different parts within it interact with each other to carry out functions. Something important to note here, however, is that UML allows us to abstractly render these components. So what that means is that what is displayed here is simpler than what is actually was actually within the fully implemented system. So that means that we can show simply how this system is arranged more broadly, while while keeping you from having to see the minutia of how this system is actually composed. But that being said, we can go ahead and discuss the responsibilities of this system. That being, this is simply used to request and access resources. And so it'll do so by tracking the space and time data of the user and sending that information alongside resource requests. It'll go ahead and receive resources also if the user is authorized to receive them. For the resource server, which is pictured here, it has the responsibility of being a policy information point. And so it does this by storing resources being accessed by users, and it'll go ahead and distribute them after making authorization requests to the authorization server. If access is granted, it'll provide the resources to the mobile application. So in doing that, it's enforcing the policy of either distributing or not distributing resources. The authorization server, which is pictured here, has a responsibility of evaluating user requests, and that is the policy decision point. It'll go ahead and use the policy information stored in the authorization database, which is the policy information point, and it'll use the user's time and location in order to determine if access should be granted. And it'll go ahead and distribute an authorization token to the resource server if the SD zone is found to be valid. Now we've discussed the three main components and what each of them do. We can go ahead and discuss a realistic example of this software in practice.
All right, good afternoon. My name is Miguel Trevino, and for my portion of the presentation, I'll be looking at a demonstration of the mobile application that we've developed, as well as giving some additional functions that are available to users of the system itself. And to begin with, we're going to be looking at some what is called data sets that we've modeled after a software development company. This is just information that represents the overall components of the GSTR back model itself. As such, we have data sets that represent the users. These are just the people that can utilize the system itself. Additionally, we have the roles that a user can have within the system. We have other information, such as the time intervals that have been embedded into the system, along with the locations. Further, we have objects, which represent the resources that can be available to a user from the system itself. And lastly, we have the activities that a user may perform on an object or resource. Going further, we can then see additional data sets that help combine the previously shown sets displayed. For instance, we have the spatial temporal zones, which combine a location to a time interval in the system. Additionally, we have the permissions combining an activity to an object. User role assignment combines a role to a user under a given spatial temporal zone. And permission role assignment does the same, combining a role to a permission. Finally, we have the role hierarchy, which combines two roles in a chain of command sequence. What these data sets help us do is understand the overall relationships between the various data in the system. Using this data, we can then develop what is called an access control graph. Here we can see a small portion of this access control graph. And what I'm going to be showing is an abbreviated version of the full graph, only showcasing two users of the system. Over on the right, you can see those data sets which help represent the flow of data in the system, such as role hierarchy or user role assignment. Currently, what we can see is we have a user, Alice, who can access her role under the zone 4. And in the same, she can access the role's permission number 8 under the same zone. We can add another user, Bob, who can access his role program supervisor under zone 2. Using the data sets on the right, we can then determine that Alice has a senior role, project lead, to Bob's junior role, program supervisor, which she can access under zone 0. We can further complicate this graph and adding another role, which is a junior role to Bob, software programmer, which Bob can then access under the zone 2. Similarly, he can then access the software programmer's permissions, permission 1 and 3, under the same zone 2. Going further, we then add additional roles and can then determine that Alice can potentially have access to two separate roles in this graph. The first being software programmer and the latter test engineer. Here is where we need to denote what is called a separation of duty. This simply denotes that there exists a conflict between these two roles, such that Alice should not be allowed permissions to access them at the same spatial temporal zone. In this case, the conflict could arise because a software programmer is meant to generate code or create code, whereas a test engineer more than likely must test the limits of the code generated. As such, there is a conflict of interest and a separation of duty is denoted. Here we can see the mobile application that we've developed. This is a system that allows a user to access the system using credentials and can input various information such as their location or time interval, as well as the role that they want within the system, and the resource they want to access and the activity to perform on said resource. A user is allowed to do so using the resource server and authorization server, which house the information a user must parse through. We allow these components to interact with each other using a wireless connection such that they can communicate. I would like to also emphasize that the system is tamper-proof, and allowing a user to input their time and location is not in the final build of the application itself. And as such, the application itself should not allow a user to input these factors, and it is tamper-proof. And here I'm going to show a conflict that arose in development of the project itself, in which what we have here is a policy database. This is a database that allows a user, that contains the information that a company uses to allow for user access of their resources. And what we required was for the management of this policy database through an administrator who works under the company itself. As such, in order to allow this to happen, we've developed an external online-based website that exists to allow an administration to communicate with the policy database and manage the information found within it, and perform various actions, such that a user may be up to date with the current policy information that a company allows. This is our implementation of the web application itself, and it's an application that allows an administrator to input credentials such that they can view the various information found within the database, such as the users or the roles. Further, they can then click on these components and view the various data within it and perform actions on it to manage it, such as adding a user or removing a user from the system, and other additional roles such as checking access. In the following slides, I'll just present a brief summary of the overall presentation, as well as give some insight into our future plans for this project itself. And so in summary, the problem we wanted to tackle was the potential security risks involved in how a mobile device may access online resources of a company. In order to address this problem, we created a software architecture based on the GSTR-back model itself, and provided the implementation of this architecture in a mobile system. The technologies we used in the development of this project was the Visual Studio and C# programming language, helpful to us to allow for the implementation of the overall systems. The Unified Modeling language used to develop the diagram shown within this presentation. The Model View Controller framework, helpful to us to allow for communication between the online-based web application and the policy database itself. And lastly, Xamarin, helpful to allow for us to code within iOS or Android formatting languages. And in conclusion, the version that the mobile application that we saw in this presentation was meant for demonstration purposes and does not actually reflect the final build of the application itself. I would like to also mention that all components for this mobile application have been implemented properly into the system and are functioning as we've intended them to. And so for future work, we hope to improve the capabilities of the system overall and improve factors such as the security that it can offer, as well as its reliability and usability to those that utilize the system itself. These are our references. And thank you. Any questions?